Nice. So our schedule's here, right? Um, and so we're looking today at 4.6, number 25, min distance problem. So we'll have one just like this on the exam. Most likely I'll change the function, I'll change the point, but the process is identical. So you want to have this problem down on your formula sheet. You want to have that distance function down on your formula sheet so you know how to do this, or at least you know how to get started. So we're asking for the min distance from the y equals square root of x to the point 3, 0. And we know that distance should be perpendicular. And we're arbitrarily saying, well, that point has to be x comma square root of x. So there I've used my y equals square root of x already because that point is xy, right? So I want to find the x, I want to find the square root of x, I want to find the distance, and I want to verify the distance is a minimum with a second derivative, right? So we want to find x, find the square root of x. We want to find the distance and verify d double prime is a min, right? So a minimum should be positive, right? The second derivative should be positive at that x value in order to be at the bottom of that valley, right? So we've got our formula, d of x is delta y squared plus delta x squared. And because I've already turned my y's into x's, right, I've got my single function of x already done here. So what are we talking about? We're talking about square root of x minus 0 quantity squared plus x minus 3 quantity squared. Everyone okay here so far? Nice. So we simplify this. We don't have to, but might as well, right? So I get d of x. This distance is what? X plus x squared minus 6x plus 9. So I get that distance is x squared minus 5x plus 9. So there is my function I want to minimize. Now, I know that distance can't be 0 just by looking at the graph. I know the distance can never be negative. I know it can't be maximized. So knowing all of those things help me, right? Do you realize, do you see that? The distance can't be 0, right? Because the point would be on the curve. It can't be negative. This isn't negative anyway, right? And it can't be maximized because I could keep reaching out further and further away on the curve from that point. It'll never be maximized, right? So if I graph this, by the way, I see some kind of parabola, right? And I'll see the minimum at the base there. It's not a bad idea for me to do that because then I see what answer I'm even going to get, right? So I open up my calculator. And first of all, I'm going to just put in the parabola. Just put in the parabola. That's interesting enough. X squared minus 5x plus 9, right? And zoom standard. Nice. It looks like somewhere between 2 and 3, I get my min. Do you see that? Now, what's even more interesting now, if I square root it, so I'm going to do square root of, and watch this little trick here. Second square root. Oh, shoot, I forget. Don't tell me. oh yeah, vars, y vars, function y1. So I can just type y1 in, and it will put the parabola inside. Anyway, I go back to my graph now. There's my parabola, and here is the square root of that parabola. Do you see it's the same low point, the same x value for the low point, right? And so again, kind of looks like between 2 and 3. Remember, I can go second calculate and pick a minimum 3, and then be left of that minimum and say enter, then move to the right of that minimum and say enter, and then guess, and I could see the x value looks like 2.5, right? 2.499, but remember the calculator is a dinosaur. It's got a really little tiny brain in it. Nice. So let's get our derivative, right? So we know that the derivative of a square root is 1 over 2 of the square roots, and then times the derivative of the inside, which is 2x minus 5. There's the critical of 2.5, right? And I really prefer to write this derivative in terms of the original function. So I'm talking about 2 times d of x downstairs. Because when I do my second derivative, that makes the calculation so much easier. You don't have to do it this way, okay? You don't have to do it this way. You can keep the square root thing in there and then calculate your second derivative with it, right? It's hideous, but you can do that. So we got a critical value. Millian, do you see anything yet? Did I hit anything that's clicking or helping, or you already see where you got stuck? Nice. Was it the distance formula? It usually is, because, right, you just have to have that written down. So we have a critical value of x equals 5 halves. I can get the y value of square root of 5 halves, which is what? Rad 5 over rad 2, which is rad 10 over 2. There's my distance. I can get the distance, right? I can get the distance of 5 halves. So that's 5 halves squared minus 5 times 5 halves plus 9, all in the square root. So 25 fourths minus 25 halves plus 9, all in the square root. 25 fourths minus 50 fourths plus 36 fourths. So minus 25 fourths plus 36 fourths. Help me, 11? 11 fourths? So square root 11 over 2. There's my distance. Right? Is this okay? So remember, part of this optimization piece is, all right, first derivative, critical value, right? Verify the min or max, and answer all the questions. What was the point on the curve? What was the distance on the, right? What was the distance? And then write it all up with a nice sentence conclusion, right? A couple sentences. So we just need d double prime. So again, using d prime of x as 2x minus 5, we can use a quotient rule. Right, over the downstairs squared. And we get d double prime is 4 times d of x minus 2 times 2x minus 5 times d prime of x, all over 4d squared of x. And so why am I doing this? I know when I plug that critical value into the derivative, I get 0, right? When I plug that critical value into the derivative, I get 0. So I already know that d double prime of 5 halves is 4 times d of 5 halves over 4 times d squared of 5 halves, right? Because this piece in blue is 0 when I plug in 5 halves. In fact, it's 2 times 0 times 0. So this is just 1 over d of 5 halves, which is 1 over rad 11 over 2. So 2 over rad 11. So 2 rad 11 over 11. And that's positive, right? So if the second derivative is positive, positive people smile, I must have a minimum. And then now all I have to do is write up all of the sentences. The extra little piece I put on when I did it in class was I showed that the distance was perpendicular to the tangent line. I won't put that on the test. It's too advanced. Nora's not here, Amita's not here, Jason Z is not here, Sam is not here. Nice. Nice, that help, Million? Yeah? Yeah. And so there's one just like this on your test Friday, but it's not going to be a square root curve. It'll be some other curve. Okay? But the process is exactly the same, yeah.
So what does that say when it's d prime of x equals 2x minus 5 over 2 distance of x?
Yes, that's right. So if you see how I wrote it originally, right? If you see how I wrote my derivative originally, but notice that that's my original curve. That's my original function. So I just put the shortcut notation in for it. And when I take a derivative like implicit, it's a d prime. Yeah. And so that way I don't have to keep doing all of this algebra to make it pretty. And why do I do that? Because I know at the end, when I plug 2 halves into d prime, it's 0. When I plug it into 2x minus 5, it's 0. So I don't have to deal with all that messy 1 over 2 square roots. Yeah. Nice. I'll take homework.